Everyone, welcome to the sixth week of the live interactive sessions for sustainable transportation systems. I'm Sairi Vinayagam, PhD scholar in the Civil Engineering Department at IIT Madras. Okay, so we'll get started with an overview of the contents that were there for week 6. So in this week, we were finishing up on the transit-oriented development concept, right? So a few case studies on this transit-oriented development were covered in the first few lectures of this week, and towards the end, we looked at the planning for transportation systems, how it is done, what approaches are available. So in the first lecture, we looked at the case study of Delhi Metro, right? So this was introduced to us in the previous week, right? So this was a brownfield TOD project, right? So it was constructed in the urban area, right? And also this was not done in a field from scratch, right? So there were already developed. So this is a brownfield project. So we were looking at a particular corridor of this Delhi Metro, which is from Chhatarpur to Arganjgar, right? So this particular corridor. So what was the land use, at the time when this project was envisaged, and how it was planned, the development around this, the land around this particular corridor, right? So those aspects were covered, right? The project cost and what are the benefits that came out of it, and what are the different, alternatives that were considered. So these were discussed in the first case study. So in the second lecture, another case study of a metro system, but this was in Serbia, right? So it was in Belgrade city, which is the capital city of Serbia. So the TOD implementation again, which is a metro project for this particular city. So this was discussed. So as opposed to Delhi Metro, so this was slightly different in the sense that the how the the population was spread out in this particular city. Like whereas in Delhi it was more compact and dense. In this particular case, so it was more spread out, right? So how this low density area was planned for this TOD implementation. So that was discussed in the second lecture. And third lecture, so this was a different for a different mode. So this was for the bus rapid transit system for the Naya Raipur city. But this is different from the previous two in the sense that this was a greenfield project, right? So it was built in a land that was free, right? So it was a greenfield project, so everything was developed from the scratch. So that was the third case study for a roadway system. And with that, the TOD discussion was completed. And in the fourth lecture, we were introduced to the sustainable transportation planning aspects, right? So, what are the problems that we look to address with the planning process, and what are the main or the some of the key factors or the key challenges that we encounter, and what are some of the solutions to those, right? So, something like the parking issues, emissions, and so on. So how, what are the solutions we use or adopt to encounter these challenges? So those were discussed in lecture 4. And in the final lecture of week 6, the traditional, the conventional 4-step planning process was introduced, right? So if you recall, this the 4 steps were the trip generation, trip distribution, then the modal split, and the trip assignment, right? So what is encompassed in these different steps, right? So how they flow together, these were discussed, and some numerical examples also were provided for these different stages of the traditional transport planning, right? So that was what was covered in week 6. So now let's get into some questions related to these. So the first question is, which of the following best defines the purpose of trip distribution in transport planning? So the options are: forecasts the travel demands for a specified area. Option B forecasts the number of trips between the origin and destination in each zone of the study area. Option C is assigns traffic to a predicted model. And option D is none of these. Okay, so as usual, we'll have a poll for each of the questions. So once you are ready, you can answer in the poll. Okay, so we have one vote for option B. So let's look at the answer. So the right option is option B, forecasts the number of trips between origin and destination in each zone of the study area, right? So, so as we saw, this is the trip distribution is one of the steps in the 4-step transportation planning, right? So one of the 4 major steps is this trip distribution. So what the as the name suggests, distribution, right? So what we are doing is, so in the first step, we estimate the number of trips that are going to be generated and attracted to each zone in the study area, right? The study area is divided into different zones, and for each of these we estimate the number of trips that are going to be coming out and also coming into that particular zone, right? So there only we know how many is going out, but we do not know to which zones are these trips being generated to, right? So that is what happens in the second step, which is the trip distribution. So we distribute the trips that are generated from a particular zone, right, into different destinations, right? So therefore, so for each origin, so for each origin zone, so the total number of trips that are coming out, so we determine how it is going to be split across the different destinations, right? So that's the purpose of the trip distribution step. Okay, so A and C, so these are not in the trip distribution. They come under different in the other steps of the 4-step planning, right? Only option B. So this happens in the trip distribution step. So the right answer is option B. Okay, question number 2 is which of the following is false with respect to transportation surveys? So option A is voluminous and time consuming. Option B, the last stage in the formulation of a transportation plan. Option C, collects data on all factors influencing travel patterns. And option D, the cost involved is very high. Okay, so we have one vote for option A, voluminous and time consuming. So the right answer is actually option B, the last stage in the formulation of a transportation plan. Right. So remember the question is asking about an aspect which is false about the transportation service. Right. So one of these four options is incorrect, and that's what we are trying to identify with respect to transportation surveys. So with regard to transportation surveys, so when we are doing this, when we are doing the planning, so we need to know about the current status, right? So we need to know what is the ground conditions so that we can plan for the future better, right? So remember, we are not planning for the current step. We want to, this system once it is built, it's going to last, for a few years, right? So we cannot make changes that easily. So we want to design a system taking the future conditions into account. But for that, we first need to know what is the present conditions so that we can forecast, or estimate what is going to be the condition in the future, so that we will be able to, design for that condition, right? So to do that, we need a large, variety of data and also a large volume of data. If you are considering planning at a city level, so we will need a lot of data to be collected, right? So therefore, we will be dealing with huge volumes of data, and also collecting this is a time-consuming process. Remember, surveys there are different types of surveys. Generally, we'll go for home-based or face-to-face surveys, and these are time-consuming processes, right? So we want to collect data from multiple households, and that it takes a lot of time to gather this data. Sometimes a year or two, right? So therefore, option A is actually correct about transportation service. So it's not wrong. So it's voluminous and time consuming, right? And then option C says collects data on all factors influencing travel patterns, right? So this is also correct, because as I said, we want to predict what is going to be the future conditions, right? So we need to know the travel patterns. So to do that forecasting, to do that estimation of the future conditions, we need to collect data on all the factors that are going to influence it, right? So only when we have the data on all the factors that are responsible for people's travel decisions, we will be able to get a reasonably accurate estimation of the future trends, right? So therefore, we try to collect as much factors as possible that influence the travel pattern. So C is also a correct statement, and D is the cost involved is very high. This is also true. Like as you can imagine, when we are dealing with huge volumes of data, and also like there is a lot of manpower that is involved, right? So therefore, there is a cost component also, which is high, because we are dealing with large volumes of data, and also doing this for a long period of time. Therefore, the costs are also very high, right? So therefore, D is also a correct statement about the transportation service. It's only option B that is not correct. So it says that the transportation survey is the last stage of the transportation planning. So that is incorrect. Why? Because before, when we want to do the planning, survey has to be one of the first steps, right? Because based on the current conditions only, we can determine the future. We can get an estimate of the future state, and then we can plan or design for that, right? So this cannot be at the last stage. This has to come, before we are at the start of the planning process, right? So only then we would be our, designs all will be, correct. Therefore, this cannot be in the last stage. Therefore, this is an incorrect statement of transportation service. So the right answer is option B. Okay, question number 3 is, which of the following is not a sustainable transportation planning solution? So the option A is park and ride facility. Option B, shared spaces. Option C, uninterrupted bus lanes. And option D, automobile centered planning. Okay, so we have one vote for option D, automobile centered planning. Okay, so the right option is also option D, it is automobile centered planning. So the question is, which of the following is not a sustainable transport planning solution, right? So for it to be a sustainable transport planning solution, so it should, meet all the goals that we have, set out for a system to be sustainable, right? So it should have, less emissions, right? The fuel, it should be fuel efficient and so on, right? So we have to look at each of these solutions and see whether they are contributing to that sustainability aspect or not, right? So park and ride facility. So what is a park and ride facility? So it's when people want to make a trip from A to B, right? So, and if it is a long journey, so instead of, using their personal vehicle to cover the whole journey, what they can do is take the personal vehicle and go to the nearest, transit station, park the vehicle at the transit station, and then catch the train or bus or whatever is the transit facility available, and then reach their destination, and then, finish their work, come back and take the parked vehicle and go back home, right? So that's what the park and ride facility is. So what is this enabling us? So this enables or encourages people to use the transit system, right? So the majority of their trip, the longest, part of the trip is covered using a transit system, right? So therefore, this, encourages people to use the transit system more, and, not use their personal vehicle for their complete journey, right? So this reduces congestion and, reduces the emissions and so on. Therefore, this is a sustainable solution. Option B is shared spaces. So shared spaces refers to, the use of the transportation system by different like modes, right? For example, we could have dedicated lanes for buses, along with, separate lanes for, biking, and so on, along with, the lanes for car traffic as well. So we are, providing the facility for all the modes. So this also again encourages people to use these, reduce their dependence on private vehicles, and, take, NMTs also as one of their, modes of travel if it is feasible, right? So therefore, this also encourages people to reduce their dependence on the automobiles. And C is uninterrupted bus lanes. So this is like providing a dedicated lane for buses, right? So no other mode of vehicle can use that lane that is designated for buses. So what does this help? How does this help? So this will, reduce, the travel times for buses, because now they are not interacting with, the other modes of transport. So therefore, their travel times will be reduced. There will be lesser delays for buses. So therefore, the travel times will be more reliable, and people will be encouraged to use buses more, right? So because they don't have to, wait for long, the buses will come on time and so on. So therefore, this will also help, moving towards sustainable system of transportation. Whereas option D is automobile centered planning. So automobile centered planning means So, for example, if you are going to plan your systems focusing on automobiles, like designing it for people who will be using automobiles or cars more. So what happens in that case? You'll be providing wider roads, with multiple lanes, and what this induces is for people to use more of their private vehicles, right? Because the roads are wider, roads are there, so people will be more encouraged to buy their own vehicles and private. So in the long run, this will add to more congestion, right? More pollution and so on, and therefore this is not sustainable in the long term, right? So therefore we should not go for an automobile centered planning. So this is the option that is not sustainable out of the four. Therefore, the right option is question number 4 is which of the following is true in the case of a transit oriented development approach? Option A is station area, then community zone, then transition zone. Option B, community zone followed by station area, then transition zone. C, station area followed by transition zone, then by community zone. And option D is the transition zone followed by community zone and station area. Right? So basically, we want to arrange them in the right sequence as we see from a transit station, right? So as we go away from a transit station, what is the sequence in which these different areas or zones are observed in a transit oriented development approach, right? So that's what we want to find out. So we have to find one of these four options which is correct. Okay, we have one more for option D. Okay, so the right option is actually option A, is station area followed by the community zone, then by the transition zone, right? So if you look at this figure at the bottom, so this particular place, right, shown by this gray rectangle, so this is like a typical, some transit station, right? And we want to, arrange the three, zones, as the in the order that we will observe them as we move away from this transit station. So as we can see here, so this region around the transit station is divided into three zones. So one is the urban station quarter or the station area. So which is the distance of about around 500 meters as we go away from the transit station, right? So then we will be encountering the community zone, right? So which is again between 500 to around 1000 meters, and after this 1000 meters we will be encountering the residential and the transition zone, right? So the correct order is that first it will be the station area. So the area that is in the immediate in the vicinity of the station, followed by the community zone, finally the transition zone. Therefore, the right order is given in option A. Okay. So question number 5. The line used to represent the physical or natural barriers of a study area for the purpose of a transport planning survey is termed as dash. So the options are internal cordon, external cordon, screen line, none of these. So we have one vote for option B. We have one vote for option B, external cordon. Right, so the right answer is option C. It is actually screen line. Okay, so basically, if you look at it, transport planning survey, so we'll basically have a study area, right? So suppose if this polygon represents the study area, then like we'll have two types of lines, so we cannot collect data for this whole region as a whole. So what we will do for for the ease of the study, so we will be trying to divide this region into different zones or different parts. Okay, so it could be done in any order, so based on the purpose of the study, right? So we'll be using some lines to demarcate this into different zones, right? So and also it's not like we'll just use that. So there are sometimes we will use, if there is a, say there is a a natural barrier. For example, there is a river that is flowing through the city. Suppose this blue line represents a river. So what we will take this river as a boundary of a particular zone that we are interested in. For example, we have this red line that is a boundary that we are interested in. So we will take this river also as one of the boundaries, and then define, for example, maybe this particular region as one of the zones, right? So we could divide the area like that. So this such physical barrier. So this river is a physical barrier, right? So such physical or natural barriers, these are called as the screen lines, right? So this help us provide a demarcation of this the boundary of the study area, right? So the other lines, the imaginary lines that we draw ourselves to demarcate, so those are called the cordon lines, right? Whereas this natural or the physical barriers which form a boundary of the study area, so they are called the screen lines, right? So here we are looking the question is asking about this particular physical or the natural barriers, so that is the screen line. So the right option is option C. Okay, now question number 6 is, which of the following options is correct in Delhi city's transit oriented development, that is TOD? So option A is Greenfield Urban TOD, option B is Greenfield Suburban TOD, option C is Brownfield Suburban TOD, and option D Brownfield Urban TOD. Okay, so we have one vote for option D, Brownfield Urban TOD. So the right option is it's a Brownfield Urban TOD, right? So we looked at this particular Delhi city's TOD case study, right? So we in the last week we saw what is the difference between a brownfield and a greenfield project, right? So greenfield projects, so they are built built from scratch in an area where there is no pre-existing developments, whereas brownfield projects, so these are projects that are accommodated into an area where there is existing developments, right? So in the case of Delhi city's TOD, that is the Delhi metro system, so this was a brownfield project because this was constructed in the Delhi's urban area where there were already developments that were existing, right? So this was added on top of it. So therefore, this is not a greenfield project; it was a brownfield project. And between urban suburban, this was in the urban region of Delhi, right? So therefore, this is a brownfield urban TOD project. So the right option is option D. Okay, question number 7 is the traditional four-step transport planning process in the correct sequential order is option A, trip distribution, then trip generation, modal split, and trip assignment. Option B, trip generation, trip distribution, modal split, trip assignment. Option C is trip distribution, trip assignment, model split, and then trip generation. Option D is trip generation, trip assignment, model split, and trip distribution. So we have one vote for option B. So the right answer is also option B. Right, so it is trip generation, distribution, model split, and trip assignment. Right, so this four-step planning process, it was covered in the the fifth lecture of week 6, right? So that's where we were introduced to it. So the four steps, as we can see, are the generation, distribution, model split, and trip assignment. And this is also the right sequence. So this has to be done in the correct sequence, right? So first we will do the trip generation. So as we discussed, so trip generation is where we try to estimate what will be the total number of trips that will be originating and also ending in each zone that is within the study area. The trip distribution is, so once we know how many trips are going to leave a particular zone, so we will be trying to determine to which zones they will be leaving to, right? So that is the trip distribution step. And the third step is the modal split, where we are trying to determine what is the percentage share of these trips that are that are having that are going from zone A to zone B. So out of these trips, how many will be public transport trips, how many will be private trips, and so on. So that is the modal step split process. And in the final step, we will do the trip assignment, which is to assign these different modal trips onto the routes in the road network, right? So that is the trip assignment process. So this completes the whole planning process. At the end, we will know what will be the volume of traffic on the different links of the network, right? So that is the ultimate goal. So therefore, the right sequence is B. So generation, distribution, model split, and trip assignment. Question number 8 is, a city with a population of 4,584 generates 11,460 trips per day. What would be the trip rate of that city? So the options are 0.4, 2.0, 1.2, and 2.5. Okay, so we have one vote for option A, 0.4. Right, so the right answer is actually option D. It is 2.5, not 0.4. Okay, so let's take a look at how to derive that. So basically the question is to derive or find out what is the trip rate. So what is trip rate? So trip rate is nothing but the number of trips generated per person per day, right? So how many trips will a person make in one day, right? So that is what we call as the trip rate, right? So what is the information that is given to us? So so what we know the total population of the city, which is 4584. And we also know in one day what is the total number of trips that are made by everyone in the city, which is 11,460, right? So our goal is to find what is the number of trips a single person will make in a day, on an average, right? So that's what we want to find. So how will we get that? So to get the trip rate, so what can we do? So we'll take the total trips generated in a day divided by the population of the region, right? So if we do this, we will be able to get the trip rate, and we know both of these quantities, right? So what is the total number of trips? So which is 11,460, and then the total population is 4,584, right? So 11,460, 4,584. If you divide that, so you will find that this comes out to be 2.5, right? So therefore 2.5 trips, per person per day, right? So this is the trip rate for this particular city that is given in the question, right? So on an average, we can expect every person to be making about 2.5 trips in a day, right? So therefore that is the trip rate. Okay, any questions? Okay, so moving on to question number 9 is, if the land use of an area can be changed easily in terms of regulatory procedures, it can be termed as dash. Option A, hard land. Option B, moderate land. Option C, soft land. And option D, none of these. Okay, so we have one more for option D, none of these. So the right option is option C, it is soft land. Right, so basically we have these three terms, so which we'll use to classify the land that is around a particular corridor that we are trying to develop, right? So for example, we have a transit corridor plan. So around this, we'll be planning not only this particular corridor, but also the land that is surrounding this particular corridors, right? So we could have different fragments of land belonging to different land uses, right? So it could be, for example, if it is like a government property, right, and we are also trying to do a government project, right? So this metro systems, all these transportation systems, they will be developed by the government as a public property, right? So if it is a government land that is a company that is on the along this corridor, so those lands can be easily acquired and then used for developing this transit system, right? So it is easier to change them. So those kinds of areas are called as the soft land, because it is easy to change the land use for the purpose of this transit development, right? So therefore it is called soft land. So there could be other types of land uses. For example, if it is a privately owned land, right? So some private landowners are there, If it belongs to them, then in that case it is not easily changeable, the type of land, because they would be using it for some purpose, and but we may need it for a different purpose for our particular development. So in that case, we need to get the land from this private landowners and then modify it for the our case, right? So which they may not readily agree to do it, right? So therefore, these kind of but it is still possible if once we make them agree to it, right? So by compensating or getting them or bringing involving them in the project and so on, so we can it is possible to do that. So those kind of lands are called moderate land use. And then there is the final one, which is hard land. So hard land is, for example, it cannot be changed, right? So we cannot change the land use. For example, if we have some military establishments, right? So some strategic defense locations, so those things we cannot change the type of land use, right? So those are hard land, right? So therefore the answer for this question is about it, because it's asking about land use which can be easily changed. So therefore, it is a soft land, right? So because it is easily changeable. So right option is option C. Okay, question number 10 is, if the size of a plot is 500 square feet with land coverage of 70% and the floor area ratio FAR is 10, then the maximum number of floors allowed for construction is dash. So options are 7, 14, 21, and 28. Okay, so we have one vote for option. So we have one vote for option A, 7. So right answer is also is actually option B. It is 14. Okay. So how do we get this? So let us see. Okay. So the question is, so we know there is a building, that is going to be constructed on a 500 square feet plot. Right, so the land coverage is only 70%, right? So we can only use 70% of this area of 500 square feet for building the for building purpose, right? And then the floor area ratio is also given as 10. So we have to determine how many floors can we construct on this piece of land, right? So how do we do this? So first, let's understand what is the floor area ratio, right? So the floor area ratio is nothing but the ratio of the total area, the total floor area constructed divided by the size of plot, size of plot or land on which the construction, uh, you know, um, right? So this is the floor area ratio, the total floor area that is constructed over the size of the plot on which the building is constructed, right? So what do we know from the question? So we know that the floor area ratio is 10, right? So that is given to us. So also the size of the plot is also known, which is 500, right? 500 square feet, right? So now we need to determine what is the total number of, or the maximum number of floors that we can build, subject to this land coverage as well as the floor area ratio. So suppose we are constructing n floors. So let us keep that n as a variable. So n times the total floor area is nothing but if the area of one floor is some x. So and then the total floor area is n into x, where n is the number of floors that we have constructed, right? So each floor is assuming they are of the same area. So if you build n floors, so the total area will be n times the floor area of one floor, right? So what will be the floor area of one floor? So we know that the land coverage is only 70%. So 70% of the plot size is the area of one floor in the building, right? So 0.7 into 500, which is 70% of 500 is the floor area for a single floor. And if we build n floors, the total floor area will be n times of that, right? So that is the total floor area. The size of the plot is 500 and floor area ratio is 10. Right? So from this, we'll be able to find out what is the maximum number of floors that we can build. So basically 500 and 500 will get cancelled. So n will be nothing but 10 by 0.7, right? So this is approximately 14, right? It's 14 point something. We cannot have like fractional number of floors. So rounding it down, so it will be approximately 14 floors. So the maximum number of floors that can be built on this particular plot, subject to this floor area ratio constraint is 14 floors, right? So right, because we cannot cover the 100% of the plot, the land coverage tells us what is the maximum area on which we can build, right? So some more than 70% of this land cannot be used for building, right? So subject to that and the floor area ratio constraints, so we can build only a maximum of 14 floors on this particular plot. Okay, any questions? Okay. Okay, so moving on to question number 11 is, which of the following is true with respect to trip distribution in an ideal case of transport planning? So options are A, trips generated should be greater than trips attracted. B, trips attracted should be greater than trips generated. C, trips generated and trips attracted should be balanced and made equal. And D, none of these. So we have one more for option C. So the right answer is also option C, that trips generated and trips attracted should be balanced and made equal, right? So we already looked at the trip distribution process, right? So what is the trip distribution? So we have a certain number of trips that we know are generated and certain number of trips that are getting attracted to each zone, right? And in the trip distribution, we know from for every pair of zones, so what is the number of trips that are going to be going from the zone A to zone B, right, in that pair, right? So that's the output of the trip distribution. So what we want is this output, what are the condition that this output should satisfy, is that it should the trips that are coming out of a zone, right, and the trips that are getting attracted, they should be balanced, right? So total number of trips, so if we consider how for from each trip there is a particular number of trips that are coming out, so which is the trips generated, and if we can also count the number of trips that are entering each zone, right? So that is the total number of trips attracted, right? So this total number of trips generated and attracted, we want them to be balanced, right? So that so if we come otherwise what will happen, we'll have some trips which are not generated anywhere, right? Or we'll have some trips that are generated but not going to any zone, right? So that will not be logical, right? So therefore we try to do this trip distribution in such a way that if we sum up the total number of trips generated across all the zones, so they should be equal to the total number of trips that are attracted to each zone, right? So therefore our distribution will be more logical, right? So therefore we want condition C to be satisfied in an ideal case, right? So that's what we will do in the trip distribution process, right? So therefore C is the right answer. Okay, question number 12 is the dash is similar to the concept of Newton's law of gravitation. Option A is a growth factor model. Option B is a gravity model. Option C, Tanner model, and option D is none of these. Okay, so we have one vote for option B, gravity model. So the right option is also option B. It is the gravity model, right? So the names give away, right? So Newton's law of gravitation and gravity model. So, but why is it same? So, what is from the Newton's law of gravitation? What do we know? The force, the gravitational force, is proportional to the mass of the two bodies, that are being attracted, right? It's directly proportional to the mass, is product of the two masses, and it is inversely proportional to the square of the distance. If r is the distance between the centers of the two masses, then it is inversely proportional to the square of the distance between the two, right? So that's the Newton's law of gravitation. So out of these different models, so the gravity model also has a similar form. So in which where we use this is in the trip distribution stage, right? So if the trip interchange or the trip between zone I and zone J, right? So remember this distribution is for a pair of zones, right? So how many trips are going from a zone I to zone J, right? So if we represent that as TAJ, then what this gravity model tells us is this is directly proportional to the product of PI and AJ. Okay, so what is PI? So PI is the total number of trips produced from zone I, and AJ is the total number of trips attracted to zone J, right? So it is the product of these two quantities. So it is directly proportional to that and inversely proportional to some a function f of some small Tij. Okay, so what is this small Tij? Small Tij is nothing but the travel cost, right? So generally we'll use travel time as one of the cost factors, right? For if people are making them, but there could be other factors which can be an impedance to travel, right? For example, cost, right? So if the cost of travel is high between two zones, then we can expect the number of trips between those two zones to be lower, right? So if travel time is large, can expect the number of trips to be lower between the zones, right? So there could be different factors. So this f of Tij is a factor, is a function of this impedance, right? So it's an impedance function to that trip between the two zones, right? So generally this will be a nonlinear function of this cost, right? If you look at it, these two functions are very much similar to each other, right? So the number of trips that are distributed between two zones is directly proportional to the productions or the trips that are generated, and attractions which are getting attracted to the zone J, and inversely proportional to a function of the impedance, right, which is generally non-linear, right? So therefore, this gravity model is very similar to the Newton's law of gravitation. So the right option is option B. Question number 13 is, if the land use of an area cannot be changed, it will be termed as dash. So options are hard land, moderate land, soft land, and none of these. Okay, so we have one more for option A, hard land. So the right option is option A, hard land, right? So we already saw what these three different terms mean: hard land, moderate land, soft land, right? So we already saw the definition of soft land, which is the land which can be easily, the land use which can be easily changed based on the regulatory requirements. Moderate land, it's not easily changeable, but it is possible to do that, right? So because by talking to the private parties and so on. Hard land is something that cannot be changed, right? So whatever is the current land use, that will be what it will be. So we cannot change it for our purposes, right? So therefore, here the right option is option A, hard land. Question number 14 is, if the size of a plot is 1,000 square feet with the land coverage area of 50% and the number of floors constructed is 10, calculate the floor area ratio. Okay, so the options are 5, 10, 15, and 20. So we have one more for option B, 10. So the right answer is actually option A, it is 5. So Let's see how to get the answer. Right, so we want to find out the total floor area, the floor area ratio FAR. So as we saw earlier, so this is nothing but the total floor area divided by the size of the plot, right? So what is the size of the plot? It is 1,000 square feet. And what is the total floor area? So how do we know that? So we know the total number of floors constructed, which is 10, right? And also it is constructed on a size of plot 1,000 square feet with a coverage area of 50%. So what does that mean? Only 50% of this plot size can be used for construction. Right? So the size of one floor is 50% of 1,000, which will be 500 square feet. Right? And we have 10 floors. Therefore, the total floor area will be 10 times 50% of 1,000. Right? Right, so that will be the size of one floor. 0.5 into 1,000 is the size of one floor. We have 10 floors, so 10 times of that, so that is the total floor area of the building. And the size of the plot is 1,000. So again, so if we just simplify this, so 1,000 and 1,000 gets cancelled, so it is half of 10. Half of 10 is 5, right? So that is the floor area ratio, right? So therefore the right option is, okay, we have the same concept that we saw earlier, but instead of finding the number of floors, here we know the total floor area already and also the size of the plot. So directly we can calculate what is the floor area ratio. Okay, is that clear? Any question? Okay. Now moving on, question number 15. The imaginary line used to represent the external boundary of a study area in transportation planning is termed dash. So options are A, internal cordon, option B, external cordon, option C, screen line, and option D, none of these. Okay, so we have one vote for option B, external cordon. So right option is option B, it is external cordon, right? So as we already discussed, what are these two terms, cordon line and screen line, right? So basically they are lines or boundaries that used to divide the study area into different zones, right? So as we saw earlier, so this is the study area, so we could divide this into multiple ways, right? So we can divide them into different zones based on the purpose that we are carrying it out for. Okay, so these lines that I'm drawing here, so these are imaginary lines across this study area that is dividing it into different zones, right? So we have we can basically say there are two types of these imaginary lines. So one which tells us what is the outermost periphery of the study area, right? So that is the external cordon line, right? And then the lines within that study area. So these are the internal cordon lines, right? So here we are talking about the external boundary. So the external boundary is given by the external cordon line, right? So therefore the right option is option B, right? So whereas the screen line, as we saw earlier, it's not the imaginary line, but it is based on some physical barriers that may already be running through. For example, if we have a railway line, so we could use the railway line as one of the boundaries that we can use within the study area. So that will come under the screen, right? But these imaginary lines that we use, they are the cordon lines, and the outer boundary is given by the external cordon line, and the inner demarcations are given by the internal cordon lines. So here the right option is option B, external cordon. Okay, question number 16 is, which of the following has the highest residential area percentage in transit oriented development? So option A is station area, option B is community zone, option C is the transition zone, and option D is none of these. Yeah, so we have a vote for option C, transition zone. So the right option is option C, it is a transition zone. So as we already looked at these three different zones or areas, so we have the transit station, and in the immediate vicinity we have the station area, right? And then farther from that is the community zone, right? And then away from that is the transition zone, right? So this transition is also called as the residential transition zone, right? So as we can see from the figure that is given here, so what we have, so near to the station, that is in the station area, so we have, if you look at the different types of land uses, see these boxes, they represent the white boxes, they represent the residential buildings, right? So the other colored ones represent different buildings for different purposes, such as schools, clubs, other open spaces, and so on, right? So if you look at it within the station area, we have a lot of these other land uses that are available. Relatively, the residential land use is lesser, right, in terms of the area that is occupied. So whereas if we go farther away into the community zone, so then we can see that there is more number of residential buildings that are available, and the less of these commercial or other uses of the land. Whereas if you move further away into the transition zone, here we see that it is primarily for the residential purpose, and so therefore the other activities that are taking place in these zones are very limited, right? So therefore, this is the region where we will find highest percentage of the residential area. Therefore, the right option is option C. It is the transition zone, right? So it is relatively having the higher area in terms of the area occupied by the residential land use, right? So therefore, the right option is option C. Okay, question number 17 is, estimate the trip rate for residential land use and its population is 5,000 and the number of trips is 14,000. The options are 0.36, 0.18, 2.8, and 5.6. So yeah, this it was answered in the chat. So it is 2.8. So the right option is also 2.8, right? So how do we get this? So we already saw how to calculate the trip rate. So trip rate is nothing but the ratio of the total number of trips, right? So total trips over the total number of people or the population of the region, right? So here we know both of these. So the total number of trips produced in a day, so that is 14,000, right? And then the population is 5,000. right? So therefore 14,000 by 5,000, so that will give you 2.8, right? So that is the number of trips on average a person makes in this particular region, right? So therefore 2.8 trips per person per day is the trip rate. So option C is the right one. Question number 18 is, which of the following has the highest floor area ratio in transit oriented development? So the options are station area, community zone, transition zone, and none of these. Okay, so we have one more for option A, station area. So right answer is also option A. It is the station area, right? So why is the station area having higher floor area ratio? Right, so remember, one of the goals of the transit oriented developments is to have high density compact regions in the influence zone, right? So why do we need that? So when we have a high density region, so which means that more people can stay in that influence zone, so where the transit station is more easily accessible using non-motorized modes, right? So people can just walk to the station because it is close, and then use the transit to make their trips, right? So therefore we try to have high density region. So as you can see from the legend given here, so this red line, so they mark the 300-meter zone outside from the station area. So in this we have very high densities, and also the next 200 meters also having a high density, right? So this is coming under the station area. So these are high density regions. So going away from it into the community zone, we have medium density, right? So for the next 500 meters, and moving up further away into the transition of the residential zone, we will be having a low density development, right? So there will be more, we will have very few multi-story buildings and so on, right? So therefore this high density buildings, so when there are high density, so how do we achieve this high density? So within the smaller 500-meter region, if we need to have high density, which means we need to have higher floor area ratio, right? So when we have higher floor area ratio in the smaller region, then only we'll have a high density, right? So therefore here, if you look at it, that typically it will be in the range of 6 to 7, right? So which means 6 to 7 floors will generally be seen in this particular region, that is in the station area. As we go away from it, so the floor area ratio will reduce, right? So it will be in the range of 3 to 4 in the community zone, and 1 to 2 in the residential transition zone, right? So as we can see, the density drops as we move away from the transit line, right? So therefore the highest FAR is in the station area, so that is in the option A. Okay, so question number 19 is, which of the following is or are the development based land value capture method? So options are air right sale, joint development, land readjustment, and all of these. Okay, so we have one more for option D, all of these. So the right option is also option D, it is all of these. Right? So what is the land value capture? So basically, so when when we are doing a transit oriented development or any project or any other development that is undertaken, so what happens is the value of the land that is in the surrounding region will increase, right? So the government is investing in a project and it is developing that particular project. So as a result of this, the owners of the land in the surrounding region, so their land value is appreciated, right? So then, therefore they are benefited, right? So because they are benefited from this public investment, so this land value capture is basically getting this appreciated value of this land in the surrounding region to pay back for some of these investments that the government made, right? So that is the land value capture, and there are two methods in which this is done. So one is based on the tax, based on tax, and the other is based on this development method. So in the tax based method, so what do we do is a tax is levied on the surrounding commercial land uses. So whatever is the different activities that are going on, a tax is of that is imposed on the surrounding activities. So because they will be having higher activities going on because of this current project that is being developed, right? So therefore the tax will be imposed on that, and that will be coming back to the government. So that is one way of capturing the land value. So the other is the development based method. So that so again within that we have different methods, so which are given listed here. So the air right sale is basically for the development activities in the surrounding region. So the sale for doing the rights for doing those development activities are sold to different people, right? So they will be buying these rights, and then they will try to develop that area around that, and then they will be trying to use it for their purpose. So by selling these rights, the government will be getting the money for that particular piece of land. So that is the air right sale. Then there is joint development. So when people already own the land around this particular area, so they will be incorporated into this project. So they can jointly develop that particular public project that is being undertaken. Right. So because they will be benefited in the future because their land price is going to increase because of that project, so they can join and then jointly develop that particular project. Right. So that is a joint development. And third is land readjustment. This land readjustment, so they'll be trying to reorient the land use or change the land use for the purpose of this particular project, and therefore give back to this the increased land value that they are finding to back to this project, right? So therefore that is the land readjustment. So all of these methods are based on the development base. These are not the tax based method, but this is development based methods. So all these three come under that. So therefore the right option is all of these. So question number 20 is how many vehicle to vehicle conflict points are reduced with a roundabout compared to an uncontrolled four-legged intersection? The options are 16, 12, 24, and 32. Okay, so we have one vote for option C. So the right option is also option C, it is 24. Okay, so what's the question? So it is, so we are comparing a roundabout with a four-legged intersection, so which is uncontrolled, which means that there is no signal or anything. So it is an uncontrolled four-legged intersection and then a roundabout, right? So in each of these, there will be a certain number of conflicts, right? So because different, movements, different directions of movements are allowed, so there will be conflicts between these, different directions of travel, and we want to see how much, what is the difference in the number of conflict points between this uncontrolled intersection and the roundabout. Okay, so on the left we have this four-legged intersection, right? So we have the four directions of travel, so east to west, west to east, north south, south north, right? So we have the four directions. So if we look at the number of conflict points here, so from each for each direction of travel, so when they come to the intersection, there are three possible ways in which they can move. For example, if we take this, west. The eastbound approach, right? So from here, from the west they could go towards north. It's from the west they could directly make a through movement to the east, and from the west they can move towards the south, right? So the number of conflict points are, so because in this there is a conflict here, that is between the left turning traffic and the through movement, right? So because there is a weaving movement, right? So some people want to turn left, whereas some people want to go straight. So there is one potential conflict that can happen here. And similarly, there is also a right turning traffic and also the through movement. So there is a conflict that can occur between the right turning traffic and the through movement. So there are uh, two conflict points that are possible here. And also when they make the turn and then try to merge, with the through traffic that is coming from the other side, so there will be one conflict that will be happening here, right? And also the turning moment from the westbound approach, that when it is trying to merge here, so there will be another conflict that is happening here, right? So there is a two conflicts when there is weaving, and two conflicts when they are merging, right? So this is for one particular approach. So similarly in all the approaches we'll have a similar number of conflict points that are happening. So this is in the weaving and the merging at the in the approaches. So in the middle we'll have again conflict between the different movements, right? So the turning movements again will interact with the through movement and also the turning movement from the other direction, right? So there could be multiple conflict points. So if we count all of these, so we'll find that there will be 32 conflict points, vehicle to vehicle conflict points, that are possible in a four-legged uncontrolled intersection. On the other side, if you look at the roundabout, so if you can visually see that there is a huge reduction in the number of conflict points. So now because we do not have all these different turnings that are allowed, so what will have, so because everyone coming in are only can only move to the left, there is no conflict now here, right? Because everyone has to make a left turn here, so there is no conflict that arising here, that is avoided. But here we have a conflict point because there could be some people who want to turn left, some people who want to go straight or turn right. So there is one weaving happening here, so therefore there is one conflict here. Again they have to merge back here, so there is another conflict point there. So similarly in all the other approaches also we will have similar conflicts. So here we'll have in total 8 conflict points, right? So from 32 we have reduced to 8 by using a roundabout, right? So therefore the number of reduction is 32 minus 8, which is 24, right? So therefore the right option is C. We'll be able to reduce 24 conflict points if we go for a roundabout. Okay, question number 21 is, in transportation surveys, movements that originate and terminate outside of the study area are classified as dash. The options are internal to external, option B external to internal, option C internal to internal, and option D external to external. Okay, so we have one more for option D. The right option is option D. It is external to external. Okay, so we already talked about coordinates, right? So basically, if we have the study area, so let us just divide it into four zones for simplicity. Okay, so we can define that or classify the trips between these zones into four categories which are given here. So internal to external, external to internal, internal to internal, and external to external, right? So basically, so these are telling us, first it is telling us where is the origination of the trip, right? So where does it originate with respect to the study area, and then the second part tells us where it is terminating, again with respect to the study area, right? So if a trip originates within the study area, and then also terminates within the study area, so in this case we call this as an internal to internal trip, right? So that is option C here, right? And if it is originating within a study area, but it is going out of the study area, it is the destination of the trip is outside, right? So the origin is inside, destination is outside, so that is an internal to external trip, right? Then we can have the other way around, a trip that originates outside of the study area but terminates inside the study area, right? So in that case it will be an external to internal trip. So it is also possible that a trip that can originate outside, pass through the study area, and then also terminate outside. So in that case, this trip is neither originating or not terminating within the study area. Therefore, it is an external to external trip, right? So this is also contributing to the traffic within the study area, but it is neither starting or ending in the area, right? So these are the four classifications, four ways of or four types of trips that we use in the transportation surveys. So out of all the trips that we try to account for, they will be falling into one of these four categories, right? So here we are talking about movements or trips that originate and terminate outside the study area, right? So both origin and destination are outside, therefore it is an external to external trip. So the right option is option D. Yes, question number 22 is match the steps in the transportation planning process with their goal. Okay, so we have the four steps of the four-stage planning process: trip generation, distribution, modal split, and trip assignment. And we have different goals listed here. So so first is separating person trips by the mode of travel. Second, calculate the number of trips in a given area. C, estimate the traffic volume in each link of the network. And D, where will the generated trips go to? Okay, so we have four different matchings given here. So you want to pick the right match. Any answer? Okay, so we have one vote for option C. So the right option is actually option B, where 1 is matched with B, 2 with D, 3 with A, and 4 with C. So we talked about this four steps in the 4 stage planning process, right? So they are the trip generation, followed by trip distribution, then by mode split, and finally the trip assignment, right? So this is in the right sequence. So we need to now match it with the what happens in each of these process, right? So as we discussed, the first stage is the trip generation. So in which we try to estimate how many trips will be originating from each zone in the study area, and how many trips will be attracted to each zone in the study area, right? So we don't know from to where they are going or from where they are coming, but we know how many will be going out and how many will be coming in, right? So that is what we will be getting as an output of the trip generation step, right? So these are called the productions and the attractions. So, right, so where is this goal given in the list? So we see that it is the calculate the number of trips in a given area, right? So that is the goal, the number of trips that are originating, that is generated from a particular area. So that happens in the trip generation stage, right? So therefore one is matched with B. So second stage is trip distribution, right? So once we know how many trips are, totally generated from a particular zone, so the next we want to know where will these trips go to, right? So out of zone one, if 10 trips are coming in, so how many will this go to, zone one, zone two, zone three, and so on, right? So where will the generated trips go to? So that is answered in the trip distribution step, right? So we know between every pair how many trips will occur. So next, once we know how many trips will occur between two zones, right? So the next stage is the modal split, where we calculate the number of trips that will be happening by each zone, right? So remember, till this point, till the trip distribution, we are only dealing with percent trips, right? So in terms of how many people will travel between different zones. So here in the mode split, we are trying to determine how many trips by each mode of travel will take place. So which means we want to convert this person trips into vehicle trips by the type of vehicle, right? So that is the output of the modal split. And finally, once we know that how many vehicles will be traveling from different zones to different zones, so and finally we want to do a trip assignment, right? So why do we do this? Because for a given pair of zone, so there could be multiple routes through which these two zones are connected, right? So ultimately we want to know what is going to be the traffic volume on the different links. So for that we need to be able to assign these strips to different routes. So if they are assigned to a route, we know exactly what links in the network that these strips will be going on, and based on the volume we will know what will be the total volume on each lane. So to do that, we need to assign these trips, vehicular trips, onto the network. So that is done in the trip assignment stage. So 4 is option C. So that will give us an estimate of the traffic volume in each link of the network. So based on that, once we know this estimated traffic volume, so for this volume we can design our networks, right? So based on that we can design the capacity of the networks and so on. So so the output of the fourth step so will give us that output, right? So as you can see, so how each of these steps in the planning process are in sequence, right? So the output of one step will become the input to the other, and this flows naturally, right? So therefore this has to be done in sequence, and in the these are the goals of each of the different processes. So this mapping is given in option B. Therefore the right option is option B. Okay. Any questions? Okay. So with that, we are coming to the end of the session for this week. So if you have any, if you need any clarifications or doubts, you can ask. Otherwise, we can close the session here, and we'll meet again next week, next Sunday, 4 to 6 p.m. Okay, thank you for attending.